now. So today, Rahman is going to give a student talk titled Experimental Mathematics, a Computational Approach to Number Theory's Greatest Challenges. So take it away.
All right, let me start sharing my screen. All right, can everyone see my screen?
Yes.
Okay, great. So yeah, as Ajman said, this will be a talk on experimental mathematics and specifically on applications to some of the biggest problems in number theory right now. So mathematics is it's commonly considered to be the most theoretical science. I mean, its test of validity is not experiments, but rather proofs. But this is a little deceptive in some ways because the work that a mathematician does is it's still there's a lot of guesswork and trying, and in some ways, like you're doing work that's like similar to what a lab technician is doing in spirit. And so there's a lot of playing, and it's not as linear of a workflow as you might think as an outsider. And one of the most famous examples of this is the Basel problem solved by Leonhard Euler. And so this, let me pull it up so that people can actually see. I have a little LaTeX of it. So yeah, this is the Basel problem, which is the sum of the reciprocal of squares. And the series converges extremely slowly. And in Euler's time, they didn't have computers to get an estimate on what this was. And so to guess this, he had to come up with some interesting computational methods using what's known as the Euler-Maclaurin summation formula. And using this, he guessed the value is pi squared over 6, and this allowed him to then, I guess, gain some intuition on what tools to call, and he then used trigonometric functions to prove this rigorously. And since the dawn of computing, experimental mathematics has grown into a lot more. So I'm going to give a quick overview on what an algorithm is, though we won't go into too much detail on this because this is more like computer science. And so informally, an algorithm is, well, a computational procedure that, you know, it has some inputs and produces an output as desired by a problem, computational problem. And a common example is sorting an array or a vector. And here is like several different algorithms with different, like, I guess, input types. Like if the vector is already sorted, nearly sorted, randomized, reversed, and they perform differently based off of the inputs. And we will be talking more about arithmetic algorithms, so just involving arithmetic operations rather than like creating new forms of data, transposing things, and the like on the algorithms on the left. So here's a quick overview on time complexity. So based off of some algorithm and the size of each input, we can have basically a function that will dictate how much time, how many steps we need to do for based off of the size of each input. And this is the big O notation. So here we have the sorting algorithms that were previously shown, and we have the time complexity in the middle, and there's best, average, and worst cases depending on how the input, its qualities, if it was nearly sorted or not. And we can basically come up with this big O of n in the limit. Basically, after a certain x0, if we can bound the time function f of x by some g of x. So this could be linear and then it's n, or it can be quadratic and then it's n squared. And this part's not too important, the space, but the arithmetic algorithms we'll be dealing with at some point have very special space properties. So it's important to think that you can sort of define the requirements of space, like in the array. In sorting algorithms, some of them like create new subarrays, and so they take up actual space, while other sorting algorithms work in place on the array that you already have. So arithmetic algorithms, and these are essentially algorithms to compute pi. And on the right, you have their convergence, their speed of convergence. So the Viet, you can see it in red here. It's about linear. The constant in front is 0.6. The Madhava-Gregory-Leibniz series, this is an extremely slow series. It's sublinear, in fact, and 10 correct digits requires about 5 billion terms. And then the Wallace product, which, as you can see, it's the pink one on the top right. And these are all like some of the earliest found formulas for pi, but they are actually pretty slow if you look at the zoomed in picture in the top right. And so there was a lot of work done in like the 20th century to like speed these up. So now I'm going to talk a little bit about the Euclidean algorithm. And the Euclidean algorithm basically is an algorithm that, given two natural numbers, A and B, we are asked to find their GCD, greatest common divisor. This is the algorithm. Basically, it's pretty simple. I'll go over it quickly. So given two numbers A and B, we basically try to take the modulo of A with respect to B, and we get the remainder. Basically, we try to see how many times B fits into A. We get some remainder R1, and then we do this algorithm again. We recurse with B and R1. So you can see on the right an example, GCD of 2021 and 473. 2021, it breaks out into 4 times 473 plus 129. Then 473 equals 3 times 129 plus 86, and so on, till we get 43, because the algorithm terminates. Whoops. And yeah, for those that were interested, the Euclidean algorithm, the number of iterations is quadratic on the number of input digits. So it's O of n squared. And I won't prove this, but there's some analysis available online that's easily found. Whoops. All right. And so now I'm going to talk about the worst case of the Euclidean algorithm. Here on the right, we can see there's a graph showing basically for the pair XY, how much time the Euclidean algorithm will take. You can see that on the line, the diagonal, that the process finishes instantaneously. And a little bit higher up, we have a dark blue purplish line that represents the worst case, as we'll see. And the worst case is consecutive Fibonacci numbers. So for those that don't know, Fibonacci numbers is just we start with 1 and 1, and then the next one is defined as the sum of the two previous ones. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. And we can put this in like a matrix representation, and if we play around with the eigenvalues and eigenvectors, we can get a closed form out of this pretty easily, which is as follows. And it's one, like we'll see, but the limit of the two consecutive Fibonacci numbers as n tends to infinity converges to the golden ratio. And I guess one more important thing before I show the proof that this is in fact the worst case for the Euclidean algorithm. So the golden ratio is it's part of a special class of numbers, which is a PV number, Piso-Vajarov number. And these are real algebraic numbers whose Galois conjugates all have absolute values less than 1. If you don't know what a Galois conjugate is, you can just think of the minimal polynomial for your algebraic number and all the other roots of that polynomial. And it's important to know that powers of PV numbers, they approach integers exponentially. So in the case of the golden ratio, if you consider the closed form solution that I have, Fn equals 1 over square root 5, so on, you can see that the second term with the 1 minus square root of 5 over 2, that is between 0 and 1. And so as we take n higher, that will go to 0 exponentially. And so since f of n is always an integer by definition of Fibonacci numbers, you can see that 1 plus square root of 5 over 2 to the n, it converges exponentially to an integer. And these PV numbers will be pretty important. So yeah, the consecutive Fibonacci numbers, they're the worst case. And if the algorithm requires n steps to perform for natural numbers a and b, then we know a and b are at least the size of the Fibonacci numbers f of n plus 2 and f of n plus 1. So the proof is actually pretty simple. It's by induction. For the base case, it's pretty trivial. N equals 1, then b divides a with no remainders. And so the smallest numbers, natural numbers for which this is true, is b equals 1 and a equals 2, which are f of 2 and f of 3. And if we assume that this holds for all n up to k minus 1, then by the first step of the Euclidean algorithm, we break up a into q1 times b plus remainder r1. And once we recurse, we know that there's only k minus 1 steps left. So we must have that b is bigger or equal to f of k plus 1, and r1 is bigger than f of k by the inductive hypothesis. And then substituting in, we get the desired inequality below, as you can see. So this is it's pretty simple proof. It was published in, I think, 1844 by Gabriel Lemay, and it marks like the start of computational complexity theory, which is a branch of computer science. So I'm going to briefly mention continued fractions because they're pretty intimately related with the Euclidean algorithm. So on the left, we have the Euclidean algorithm example that we were just going through. And then on the right, we take 2021 over 473. And we see how many times 473 breaks into that. We put it into improper fractions. And we take 1 over the, the non-integer part. And we keep repeating this process. And once this, so once that process is finished, I don't know if you saw, we got, I'll just bring it back. So you can see that 4, 3, 1, 2, those correspond to our Q's on the left for the GCD. And rational numbers always have a terminating continued fraction, while irrationals, you can apply this process to irrationals, and you'll see that they don't. But they do certain classes of irrational numbers. they do have regular representations as continued fractions. In fact, if you ever take Mat 311, you prove in it that all the quadratic irrationals, they have repeating continued fractions, or eventually repeating continued fractions. And in fact, the transcendental constant E has a continued fraction whose coefficients follow an arithmetic progression in some sense. And I showed for the golden ratio, the continued fraction process. It basically entails rationalizing the denominator. And this is how it goes for any quadratic irrational. You can just follow the scheme. And you can see that, well, the coefficients for the golden ratio are always 1. And this is why, in some sense, the golden ratio is the most irrational number, because its convergence is as slow as it gets. And in fact, there's several theories in number theory that go deeper into this, but we won't be covering those. So we're going to be looking to try to generalize the Euclidean algorithm to more variables. And the approach we'll take is we are given a vector of real numbers, x1 through xn, and we want to find a collection of integers, ai, such that, well, their dot product will give 0. And in the case of n equals 2, this just becomes the Euclidean algorithm again. You can show the relation of this pretty easily. But turns out generalizing the Euclidean algorithm is it's extremely hard. And there's many different attempts to do it. Some have useful properties, but don't have other ones that others do. And the Euclidean algorithm it's pretty special. It's what's called a greedy algorithm. And I won't go into too much detail, but basically at each step of the Euclidean algorithm, we're basically filling up as much as possible the larger number by the smallest one. And so we are sort of like choosing the local maximum, if you will, at each step. And yeah, this is what denotes a greedy algorithm. And the generalizations we will be looking at, they aren't greedy algorithms. We're going to be looking at the PSLQ algorithm developed by Hallam, Ferguson, and David Bailey. And another interesting one is Lenstra-Lovatz, but I won't be really talking about the implementation much. I might bring up an example at the end of a number theory application if we have time. On the right, you can see this is the umbilical, I think it's called a umbilical torus. It's the statue in front of the Math and Physics building. This was actually commissioned by the Simons Foundation. They got Hallam and Ferguson to make this. He's both an architect and a mathematician.
So I have a question.
Yeah.
So about the generalized Euclidean algorithm, what is the output of that? So like in the Euclidean algorithm, the output is the GCD. What is the output for the generalized Euclidean algorithm?
So for the PSLQ and for LLL, and in fact, these all solve what's called the integer relation problem, I think, or it's something related to that. And basically, we're trying to find an integer relation, which is the vectors A1 through AI, and that's what the algorithm will output, such that this sum will be 0. Did that answer the question?
So you're inputting a sequence or a list of n numbers, and you're outputting another list of n numbers, such that their sum is equal to 0.
Yep.
Okay.
If you've heard of Bezo's identity, Bezo, I don't know how to pronounce it, but it's solving that.
Yeah.
Oh, okay, I see. Right. Okay, so it's not. Okay, I get it. Yeah.
So I quickly want to touch upon what a lattice is, because that's sort of what we're playing with, since the vector that we're outputted is they're always integers. I mean, we're solving for integers. And a lattice is, I mean, for a basis of Rn, we want to find the subgroup of the linear combinations with integer coefficients. And this is isomorphic to Zn. If this doesn't make sense, this is actually like, it's pretty easy to visualize a lattice. I have some pictures coming up. Yeah, so you can just see in the two-dimensional case that we can take two like vectors that and basically they form like a tiling of the plane. You can view it as that. And two different lattices, if the transition matrix between the bases is in the group SLNZ, then they are basically equivalent, and this just corresponds to change of coordinates. So I'm going to do a very top level overview of PSLQ. Like I said, my main goal is the number theory applications, so we're just going to breeze by this. So yeah, as I was discussing, the input is vector of n real numbers, and output is vector of n integers. And in case no relation is found, then PSLQ will return a lower bound for the norm of any potential integer relation. And so the name PSLQ actually informs us on what is happening. We're going to be using partial sums and an LQ decomposition, which is decomposing a matrix into a product of a lower trapezoidal matrix and a unitary matrix. And a unitary matrix, if you don't know, is I think it's where the inverse of the matrix is equivalent to the transpose. So we can assume that our X has norm 1, or we can normalize by the Gram-Schmidt process. And then we consider the partial sums that are defined as follows in the top right. And then take the following n by n minus 1 matrix. And it can be shown that this matrix has orthogonal columns and is orthogonal to X. So that basically the columns form a basis for the relations of X. This is the crucial relation I was, well, the bound on the norm that I was saying. That, or well, let me see. Yeah, this is the bound on the norm. I just relabeled them to A to M. And so we iteratively produce matrices A and Q by the LQ process and try to basically we want to minimize a vector. We want to minimize a vector y that is it's equal to the vector x that we were given, and the sequence of an matrices, well, their inverse, that are generated by this LQ decomposition. And when a relation is found, then the size of the small entry of y is going to drop by an enormous amount. And that's, you can think of that as a confidence level in some ways for your results. And I have here plotted the logarithm of the drop. You can see that even with a log scale, it's quite like a steep drop. So some I guess some easy applications of the PSLQ algorithm to first gain some intuition on what can be done. So we can, oh, I should have relabeled X here, but oh no, it's fine. Yeah, so given a number X, like any real number X, we can take the polynomial basis. So 1x, x squared, dot, 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 xn, and we can try to find an integer relation to see if it's algebraic, the number X. And if it is, then we can obtain its minimal polynomial in the form of our integer relation A1 through AN. And if not, then we just get bigger bounds on the polynomial degree and coefficients. There's some way to play around with, like, you know, I guess like manipulations of the Basel problem, and I guess the Riemann zeta function, and trying to see what what these sums, if they sum up to any like important like constants, such as like pi, ln2, e, and in some cases, like the one I have here, this was found through PSLQ, and then it was proved rigorously afterwards. And going back to PV numbers, so if we consider the golden ratio and take a large enough power of this, let's say the power of 48, this is a linear combination of square root of 5 and 1, but PSLQ will it'll give us some like faulty answers if we don't use like a large enough precision. And in fact, like this is like an implementation on Mathematica. You can see that I like changed the order of the inputs, and it gave me just like different answers. So like something is definitely like going wrong, and that's because well, this is the correct answer, and you get it when you you increase to 100 decimals of accuracy. But if you look at what y is equal to, it's extremely close to an integer. So yeah, the PSLQ algorithm, the PV numbers are, in some sense, they can be like worst cases. Though I'm not sure if they are the worst case, but they definitely represent like I guess like something to be careful of when applying this algorithm to mathematical work. And I'm going to be doing a quick introduction on what a number base is. I think this is like familiar to most people, but in case if. So in a base B expansion, a real number has representation x equals the sum from negative infinity to infinity of an to the bn. And in base 10, this is just a decimal like expansion that we're used to. And otherwise like binary and hexadecimal are, they're pretty commonly used in real life as well. But well, in fact, we don't need to yeah, we don't need to have b to be an integer. We can take b to be a real number and let an be just non-negative integers less than b. And we have like some pretty cool examples that whoops. I'll be talking about normality of base expansion, but there's some cool things that can be done when b is not an integer. So if you think of efficiency of the base expansion by for a number n as the number of digits needed to express n in base b times b itself, then on average, e is the most efficient base. And this is like not so hard to prove with just calculus. And there's a cool stuff that happens when you take b to be a PV number. Yeah, I won't go into detail, but if you're interested, you can look that up. So now for Spigot algorithms. So what is a Spigot algorithm? Spigot algorithm, for some arithmetic constant, transcendental constant, it allows us to get to the kth digit in a base without computing the preceding digits. So in a sense, there's no need for intermediate memory. Like in the case of our arithmetic algorithm for like the Viet or the Wallis or the other ones we looked at, there is like we're keeping an intermediate step, but with a Spigot algorithm, we can just jump to like the 100th digit if we want without computing the ones before. And the simplest such algorithm was actually known before computers existed, and that's with the natural logarithm. And I'm actually going to derive it. So we know the Taylor series for ln of 1 plus x. You can just get it by I think integrating the geometric series. And this has radius of convergence between -1 and 1. So if we play around with this, like we pull out a -1 from ln, then plugging in x equals n plus 1 over n, this will give n over n plus 1, which is in our radius of convergence, since it's smaller than 1. And we'll get this formula. ln of n plus 1 over n equals the sum. And you can see that it's pretty interesting sum, because the n plus 1 is it's constant, and then you have well, it's constant on each term. It's being raised to some power, and this will in fact be our base that we'll pick. So I'm going to cover the case where I take n equals 1, and that'll give us ln of 2. Or, well, yeah, I guess n equals for, yeah, I guess it's n equals 1. That's a typo. But that, yeah, that'll give us the case for ln of 2 over 1, which is ln of 2. And from this, we can, in fact, extract binary digits from ln of 2. So to show you this extraction, if we want to calculate binary digits starting from the 28th place, then just multiply the expression by 2 to the 27 and separate this sum into 2 parts, the positive exponents and the negative exponents. And if you remember, we only really care about the fractional part. And that is, so we can mod out from the first term. We can mod out by k, and then we can mod out the whole thing by 1 afterwards to get the fractional part we're interested in. And essentially, the second term will only affect basically the positions from the 28th and onwards. And so we can take as many terms from that as we want to get like what precision we want. So if we want it from like the 28th to the 35th, then we can take as many terms as needed to get there. And so one of the biggest achievements of PSLQ was reverse engineering, essentially Spigot algorithms for different transcendental constants. And the most famous one is the one for pi that they did. And they did this for base 16 by applying PSLQ to well, the vector up there, pi, and then x1 through x7, where each x has that form. And they ended up with the following relation. And this allows for us to calculate the kth hexadecimal digit, or the kth, like some binary power digit. And it's essentially the same way. It's done through the same way. It's a little more complicated since we have, I guess we have a more complicated rational function, but you can see the 1 over 16 to the k, that that's basically what's making this mojo work. And since then, like a lot of other BBP type algorithms were invented where the scheme is like a sum from k equals 0 to infinity over 1 b, where b is the base, to the k, and then some rational function. And a lot of these have been discovered for other rationals and bases. The one for pi was it's actually been rigorously proved. And if you're interested, I would just look up the original paper. I think it's called "The Quest for Pi" by Billy, Borwein, and Plouffe. And the proof is, it's actually, all the steps are just calculus, but they're sort of like kind of non-intuitive to come up with it if you're just like aiming to go for such an algorithm. You sort of need to like know it exists before and then work backwards from like calculus that you know. So what is a normal base expansion? So we say a real number x is B normal if every m long string, so of m digits of the base B digits, appears in the base B expansion of x with a probability of 1 over b to the m. That's not written there. I forgot it, but That's what it means to be B normal. So every M long string will occur with probability 1 over B to the M. And this was first introduced by Emile Borel in 1909 when he used a measure theoretic argument to show almost all real numbers are normal. He also conjectured that any algebraic irrational is absolutely normal, which means that it's B normal in any base. But this, in fact, has not even been proved for a single such surd algebraic irrational. The first number that was proven normal in some base was Chapernone's constant, which is just concatenating every single natural number, and it was proven to be 10 normal. And there's analogous base B Chapernone constants that were later proved to be well, normal in their base. So it's interesting that, in fact, we can get basically we can get results on normality from the Spigot algorithms, and this can be seen because the first term in this this decomposition for our digit extraction, this first term is a lot bigger than the second term. It like determines the 28th position. And for ln of 2, this is the easiest one. Basically, the first term satisfies the following recurrence, where xd equals 2xd minus 1 plus 1 over d mod 1. And this is a pretty simple dynamical system compared to like a lot of the other methods that have been used to try to like prove normality and failed. Like this seems like quite simple to work with. So it seems like there's a lot of promise with working with these recurrences. If it can be shown that this part is like equidistributed, which means that like if we take an interval a b on 0, 1, then the sequence of xd's, right, it'll be equidistributed if the number of numbers in that sequence is proportional to how big the interval AB is on 0, 1. And if we can show this dynamical system is equidistributed on 0, 1, then ln of 2 is 2 normal by a result of Bailey. And this actually happens to work for basically all Spigot algorithms, that we can create this dynamical system with the first part, and the second part is sort of an error term that we can get rid of with some analysis.
So how does the Spigot algorithm give you the dynamical system?
So you mean the derivation from the first term to like this xd equals 2xd minus 1 plus 1 over d?
Yeah.
So if we take like the next one, which is like, so okay, if we have xd minus 1, then on the next one we'll be multiplying by 2, right? There's an extra 2 because we go to d plus 1, or we go to d. And the 1 over d term, I think that comes from I don't want to say something completely wrong. So if that's okay, if you mind if I talk to you afterwards?
Yeah, it's fine.
Okay. So yeah, there's a similar like dynamical system for pi that is that you can get from the Spigot algorithm I showed before. Basically, the only thing that's different is that the second part is like a much more complicated like rational function. And if we can show this is equidistributed, then pi is 2 normal. But even with these, like at least the case for ln of 2 seems like it can be solved, but it's still an open problem in fact. Though there has been some success. In fact, this is the only success for proving a class of numbers is normal other than those like artificially like constructed constants like the chaperones. Bailey and Crandall, who are, well, Bailey is like one of the authors of PSLQ. They managed to prove the following, that given coprime integers b and c greater or equal to 2, this constant is b normal. And they also proved it is not BC normal. They used tools from ergodic theory, which is, it's an area of dynamical systems that deals with probability and making claims on almost all the phase space. And along with this, Bailey provided a Spigot algorithm for these numbers. So I guess another way to look at the normality, and this was, I found these in a paper by Bailey, in fact, is that he decided to take like these constants and say it's in like, I guess our first case is the chaperone's number in base 4. We create like a sort of pseudo random walk by saying that like in the 2-dimensional space, we divide up 2 pi into, in this case, four different angles, or we divide it by base b, and for every we like look through the constant, right? It's digits, and based off of like what number we find, we sort of go like 1 unit in that angle direction. And you can see that even though chaperone's number in base 4 is normal, you can see this sort of like fractal pattern that is like being created. So I guess that's like it's pretty interesting, because you might expect like something that's normal to produce like I guess random behavior, and it does for some cases, as you can see for those numbers Bailey proved is normal. Case A and B. And then since we showed that this number is not BC normal, then it's clear A230, where 2 is B, 3 is C, is not base 6 normal. And we can see that from the random walk. This is the random walk that's generated, and it's like pretty evident that it's very different from the base 3 and base 2 examples. So that almost like finishes the end of this talk, but I'm going to be giving like a quick overview of some results that came from the LLL algorithm. And this is related to the Riemann zeta function and the Riemann hypothesis. So if you don't know what the Riemann zeta function is, well, the Basel problem that I showed earlier was the Riemann zeta function taken for the input 2. And if we extend the domain of the zeta function by analytic continuation to C, then we get this Riemann zeta function, and it's inherently linked to the primes. There is I have this equality above that shows what's called the Euler product, relating it to the sum of reciprocals. And basically you get a geometric series from this 1 minus p to the negative s, and all the different primes together. We have all the different prime powers, and all of their combinations will give us like basically all of the composites summed up together. And there's a long-standing problem to show that the non-trivial zeros of the Riemann zeta function all lie on the line with real part 1/2, and the trivial zeros are at negative integers. This is the functional equation that Bernard Riemann he determined that the Riemann zeta function satisfies. Is written below, and this is this, you can see the line 1/2, and we know all the non-trivial zeros are in this like critical strip, the white part, but we don't have like a complete proof yet that they all lie on like line 1/2. And in fact, like there's a conjecture called the MERTENS conjecture that was an approach to the Riemann hypothesis related to random walks, in fact, as you will see. So first, consider this function, the Mobius function, defined as follows. It's 1 if so it takes as input the natural numbers. And if n is a square free positive integer with an even number of prime factors, then it takes 1. If it has an odd number of prime factors, that's a typo, it should be odd, then it takes a -1. And if it has a squared prime factor, then it takes 0. And we define the Mertens function, which is it's essentially a sum of the Mobius function up to some n. So we take the sum of the Mobius function from 1 to n. And if you know what a classic random walk is, it's that with like equal probability, we start at 0, and with equal probability, we go like +1 or -1 at each step. And this it's known that this, like, on average, the average translation from the origin is it's about like square root of n, like for n iterations of this random walk. And in fact, the Mertens conjecture was that for all n, this Mertens function is bounded by square root of n, so that it behaves like a random walk. And from the Dirichlet series above, well, if you don't know what that is, then just assume this identity, which is like 1 over the Riemann zeta function equals, like, instead of the principal character 1, we take mu n instead. And from this, we can show that if this conjecture holds, the Riemann hypothesis would hold. In fact, the Riemann hypothesis implies something a little weaker than the Mertens conjecture. So the Mertens conjecture implies the Riemann hypothesis, but not the reverse. And in fact, in 1985, Andrew Odlyzko and Hermann Terreel, they proved the Mertens conjecture false with the LL algorithm. They managed to find the existence of a counterexample between 10 to the 16 and this enormous number, 10 to the 6.91 times 10 to the 39. And no actual counterexample is known. And like, if you think about it, like normal like computational methods would have like no chance of getting to that second term, 10 to the 6.91 times 10 to the 39. So yeah, this was like this was good work that they did, because this I mean, there was like reason to think that this like Mertens conjecture like holds, right? If you think that the primes are randomly distributed, then it does lend like credence to this conjecture. And here you can see the Mertens conjecture with square root of n and negative square root of n shown as bounds. And like a lot of the computational evidence, there was an overwhelming amount of computational evidence to show that like this Mertens conjecture holds, but using the LL algorithm, they managed to show that it doesn't. So if you're interested, definitely look at the paper for that. And yeah, that's it.
Thank you so much, Riemann, for this really interesting talk. Okay, now we can have some questions.
Yep.
Anyone wants to ask anything?
So for like the ergodic theoretic proof, is that like an almost shortly statement, or is it just like do they actually show these numbers are definitely not normal, or is it like an almost surely not normal statement?
Let me go to So you mean for the 1 to the what is it? It was like ABC 0.
Yeah.
So they definitely show that all of them are normal. I do remember the theorem. I'm not sure where exactly the ergodic theory plays in. I just like remember reading that they use tools from ergodic theory, but they definitely prove that all of those numbers are ergodic. And in fact, if you saw here, I'm trying to find like where exactly which slide I had this on. You know what? I'll just leave and pull it up. I have to stop sharing somehow. Yeah, my slides are like glitched. 1 second. Shoot, can't get out.
I mean, I could share your slides. I have them, right?
Yeah, my screen is actually all black. I'm sort of having technical difficulties. Okay, here, let me start sharing my screen again.
Sometimes Zoom does that to me and it works if I double click. Ah, there you go.
So yeah, here the 0. Yeah, I wanted to say this about the 0, that this this like function of numbers, right, is taking. That they showed that ABC of 0 is equal to like this, that is B normal, but if 0 can be a parameter, in fact, and I think that in that case they showed that almost all are normal, and the parameter is added onto the exponent for b to the power c. You see the k? There should be a k plus 0 there, but if we take the parameterized version, then it's k plus like rk or something.
Okay, that makes sense. Thanks.
I think I can link you the paper if you're interested more.
That'd be cool.
Could you go back and explain the idea of the PSLQ algorithm? Because I didn't understand it the first time.
Okay. So I guess starting from this part.
I mean, where does
Or
it start?
from-
I don't know.
Okay, so we take like our vector x, right, and we form these partial sums, and then the matrix hx, the initial matrix, is constructed from these partial sums and x, and you can check that the columns are orthogonal. So up to here we're good, right?
So these partial sums are the square root of the squares of the things in the vector starting from k.
Yeah.
Okay. And then you make this n by n minus 1 matrix.
Yep.
Where the entries are, what exactly are the entries?
So they are, let me see how to explain them. They're like for the row and column ij, we take let me see, we take xi and xj on the numerator, and then just si and sj on the denominator. And then the highest diagonal is like all positives, and I think the rest are all negatives.
Oh, I was muted. Yeah. So you make this matrix and then
Mhm.
you prove that it has orthogonal columns.
Yeah, like it can be shown that as orthogonal columns.
And what does it mean orthogonal to x?
So let's see, orthogonal to X. I think all the columns are orthogonal to X. Yeah, that's what I mean by it.
Okay, so X is an n-dimensional vector as well. Okay.
Yeah, yeah.
So they form a basis of relations of X. What does that mean?
So we're going to be like, I guess we're going to be like, we're going to be taking like combinations of these orthogonal columns in a sense to try to like find a relation for X.
Why would any relation of X be a combination of these columns?
So here, let me skip to the next slide. So let's see. When we take
We're trying to find integer relations of X, right? So like
yeah,
integer coefficients that you put onto each coordinate of X to sum up to get 0.
yeah. So yeah, I think I misspoke here actually, because the I want to say that the when we do the LQ decomposition, right, and we get this integer matrix A, which A times H of X is equal to LQ of T. I want to say that the A there is in fact our integer relation, and that I was, yeah, I don't know why I wrote that X form a basis for the relations of X. Well, let me see it. Let me look at the linear algebra quickly, because I do think that I do think if we take combinations of these, then we do get like I think that A is basically determined strictly from these columns. Like our sequence of AN as we refine them is strictly determined from like our initial columns in HX. And then that like we want to find a shortest vector for the lattice in a sense, and that's the vector Y that I mentioned down here.
So what is the sequence AN?
The sequence AN is the sequence of integer valued matrices that we get from we keep on doing this LQ decomposition, and we take HX, right, and then we put it for we substitute. Let me see. Where do we substitute? Um,
Um,
yeah, one
so,
sec.
so, so is the matrix in the previous slide like you're starting
Yeah, that is our starting matrix.
and then you're trying to repeatedly update this?
Yeah,
And
I'm just trying to think which is the what's being updated. But yeah, we are continuously updating this and continuously like decomposing yeah, you know what? I do think I might have missed the updating step for the matrix H. I think that's missing from here. I think it should be right here. Give me 1 second. Trying to think about it. Well, is there any other questions? I'll readdress this in a second, but just I don't want to keep anyone waiting.
I don't hear any other questions. So, I mean,
Let me address this. Or you wanted to say something, Ajman?
I mean, it's I don't want everyone to stay here for my question if they don't want to, if they want to leave right now. So it's fine because now it's 8:40, so we can officially conclude our meeting here if there are no more questions. Otherwise, you can stick around. And Rahman, are you okay sticking around answering some of my questions?
Definitely.
Okay.
So yeah, the matrix L is our new H.